Great. Yeah. So I'm Victor, one of the engineers at RISC Zero. I work on the zkVM platform and also on cryptography. Um, so this is basically we just kind of a lot of people have been asking about zkVM performance and how to optimize guests, and we actually just released a new optimization guide. And so this study club basically is about techniques you can use to optimize your guests. So the differences between the zkVM and a physical CPU, and basically some tips and tricks that you can use to more quickly speed up your guest applications. And the kind of the big picture of like why do we care about this is our real goal here is to reduce the overall proving time and cost by making the zkVM guest code run faster. And so if your guest runs faster, the execution you have a shorter execution. If you have a shorter execution, it takes less time and energy to prove. That makes your applications run better. All of this content, as I just mentioned as well, is also available in our guest optimization guide, which is on the documentation website under the next API version. So that will be the features available will be available in the 0.20 release. But this is kind of like a preview, and a lot of the content itself about the zkVM is applicable today. All right. Another point of housekeeping before we get started is definitely feel free to interrupt at any time. Optimization is a deep and complicated topic. Cryptography is a deep and complicated topic. Optimizing a cryptographic CPU is a deep and complicated topic. So definitely feel free to ask questions at any time. So the first thing the context I want to set is, what is kind of the zkVM at a base level? And, there are many things to say about it, but one of the really kind of important things to understand is that essentially is a CPU effectively. It implements what they call an instruction set architecture, but in particular, it implements the RISC-V instruction set architecture. RISC-V is an open source ISA, very similar to x86, which is all Intel CPUs, or ARM, which runs basically all laptops, but also now all phones, but also now some laptops and servers as well. And the biggest difference between a physical CPU in your laptop or phone and the zkVM is the fact that the zkVM uses arithmetic circuits in cryptography instead of silicons and copper. So basically, it's a software and cryptography implementation of the RISC-V ISA, but it is still an implementation of the RISC-V ISA, just like any other kind of like CPU or other implementation of the architecture. And so in that sense, when you're thinking about optimization, just the first thing to think about is that the zkVM is essentially a CPU. It is a computer. And one of the main ways to kind of measure performance, especially for small programs, is in terms of cycles. A cycle or clock cycle is a single step of a CPU's execution. So basically, which is also what you see if you see a CPU runs at 3 gigahertz, then basically that means it executes 3 billion cycles per second. That's the clock rate. And generally speaking, within one cycle, a CPU can usually do a basic operation. Basic operation might be adding 2 integers. It could be bitwise operations. It could be something like that. Basically, taking 2 registers in the CPU, doing some operation, and then writing them back to an output register. So the zkVM kind of the cycle. We often use cycles per second. We use on the range of hundreds of kilohertz or megahertz as kind of our way of talking about performance. And the reason we do that is because the number of cycles that a given program uses to execute is directly related to the proving time. So a program that takes about a billion cycles to run will be about 10 times longer than something that takes 100 million cycles to run. That's because of the way that cycles translate into witness size, and witness size translates to prover time. So the general thing to understand here is basically a cycle is essentially a single step or single operation, and that the number of operations, number of cycles, is directly linked to how long the prover time is going to be. And with that, basically, we can talk about some general techniques and advice. And so I mentioned before that the zkVM essentially is a CPU, and the kind of the key idea here, just where we should start, is that in general purpose optimization techniques do work in the zkVM. So things like reducing your allocations, things like reducing the number of times you call a routine, just like reducing the work and that your program has to do in order to get its job done is always a good idea. The RISC Performance book is a great resource. Basically, it's a really good beginner-friendly optimization guide, specifically designed for RISC programming. It talks a lot about things like RISC topics, for example, how to tune the cargo and risc-v compiler, and optimization for the zkVM should basically always start by just applying common good practice techniques. Probably the most important thing to do, which is true both in the physical work, like on physical CPUs and zkVM, is to always measure your code repeatedly. You don't want to waste your time optimizing things that are not the bottleneck. If your program, if you have something that's like a super stupid algorithm, maybe it's like quadratic in time or whatever, but really at the end of the day, it only takes up 1% of your execution time. Optimizing at 10x, optimizing at 100x, optimizing at 1,000,000x will always result in a less than 1% decrease in the total amount of time that your program executes. And we'll have some more. We'll have an example of this in just a second as well. So the core idea here is like every time you're optimizing code, you always want to measure what the actual runtime of it, and don't assume that you know what the bottlenecks are a priori. And on that topic, we're going to kind of let's talk about a really simple way to start measuring your code. So basically, one of the fastest ways to start measuring your code is just to add print lines to your code. Like this is just like have it print debug statements, and you do that in the zkVM as well. And so we're actually going to start getting into an example right here to show exactly how you could do that. So I have my editor here. I wrote up a little program to use as an example. So this guess program is a regex search or a substring search, and basically it counts the number of occurrences that are in the haystack string. So this program does a few different steps that we're going to see in a second, which is one, that it reads input. The second is that it compiles the needle expression into a regular expression. Then it actually searches the haystack for the needle, counts the occurrences. Finally, or fourth, it takes a SHA-256 digest of the haystack. That basically used to say, I know a hash preimage with this number of occurrences of this substring, for instance, or this regular expression, that is. And then it commits all that to the general digest. And we can start right away by basically running this program. Some errors and flags. And we're going to run it in dev mode. Dev mode basically allows us to avoid actually proving the program, makes our total execution much faster. And just do cargo run. This is the needle, the foo, and this is our haystack. Pretty simple one right here. And so this is basically come back from the guess. There are 4 occurrences of the substring foo in the haystack that has that hash image. And other questions about this is just get started. This is kind of the baseline we're going to use for the next couple of examples. So let's start by adding some print statements. So I mentioned before that you can do this. So basically, let's say we're going to use let's see, cycles A equals in : get cycle count. And basically, this just gets the cycle counts, the cycle count at this point in the code. So we're gonna create a few different points here. Say cycles, B, C, we're going to use these basically to figure out like what the different, like how long each portion of our program is taking. So here, we're going to say eprint ln. Eprint basically just prints to the standard error. Standard error will appear in our console here. So let's see. So A to B is cycles B minus cycles A. And do the same thing down here. And run again. Oh, right. So yeah, really simple there. We can see that we have these like cycle counts now. So between each of these points, so it's like a reading input, which is A to B, takes about 6,500 cycles. Then B to A to B, which is, or sorry, B to C, which is compiling the expression, takes about 191,000. So we know that's definitely the biggest one. You can see it's much bigger than the rest. Searching takes 14,000, and then let's see, putting the digest of the haystack takes about 25,000, and then finally committing the digest takes about 9,500. So that's a really simple, like fast way to get performance numbers. And that's a good place to start, like so whenever you're working. There's a more advanced technique, and starting in version 0.2, basically have a really simple way to activate it, which is that RISC Zero supports generating pprof profiles of guess execution. And pprof is a tool that is designed for basically looking at CPU execution time. So there's a question here basically like that we could be getting some bloat from cycle count from running logic and this is called output though. And the answer is absolutely. Yeah, that definitely does add bloat to the program. And so it basically, if we're talking about orders of magnitude, like 191,000 cycles, for instance, is way above what's going to take to do the formatting and the subtraction. So basically, you do get measurement error, but the measurement error is probably on the order of, let's say, hundreds of cycles, maybe up to 1,000. But your order of magnitude for the actual work your program is doing is much higher, and so the noise basically won't compromise the overall kind of guidance of the measurement you're doing. So this is why it's kind of fast and dirty technique, because basically gives you it's easy to do. You can always kind of put those log statements in. However, basically it does not the most precise measurement and does introduce error, as Austin was mentioning. Yeah, so profiling. So profiling basically is a technique in general that is used to figure out the performance of programs. So pprof is an example of this. On Linux is also perf, the perf tool, and some other tools as well. And all these tools basically just are designed to help you figure out quickly where the where your program is going, like where the cycle counts in your where the time in your program is going. The general I definitely encourage you to read more about PROF and how it works. But we'll see what does in just a second. I'll give you an example. In RISC Zero supports today, as far as in 0.19, if you want to use it, a profiler. And then 0.20, we are going to release changes that make it much easier to access those profiles. I'm going to show off how to use the new API in 0.20 using the build of RISC Zero off the main branch of our monorepo. But basically, that kind of sums up to setting an environment variable and get a profile out. And I'll show you what these profiles look like. So going back to this code here, I'm actually going to remove all these changes. So now we're back to now that the logs have gone away. And we're going to run the same command again from before, but we're going to set RISC Zero pprof out equals profile.pb. So basically, this is telling RISC Zero and the client to basically when it runs, it will record information about the execution of the program and write it to this profile.pb file as output. So run again. And so now we have this profile.pb file. And bundled with the Go language, Google includes the pprof tool. I've looked for another way to install it. Unfortunately, though, installing Go is the best way to do it. So basically, in order to access this tool, your recommendation is to install Golang, which this tool comes with. And it's a really great tool. It can be used for profiling of any kind of application, not just building, to be clear. So we're going to run it in HTTP mode. So basically, it runs a local server and lets you look at the output. And it's going to open up the profile. This graph view is really helpful. It's a great view to use, but it's also a little bit harder to parse right away. So we're going to go over to the flame graph view. This flame graph basically, this is a view of the call stacks in your application. So basically, it starts from the top, which is the root and main here, and it goes all the way down to the roots. So basically, it starts with the leaves, which is exactly where your program is spending its time. So you can see here, for example, it's spending its time, let's say, in the drop implementation, in regex syntax, HIR, concat. Basically, these are all kind of functions deep within the regex library, which we use in our Gus code here. So use regex. And it's showing us basically where things are going. And if you hover over each of these bars, you can see how wide they are. So for example, the root is 265,000 cycles, which is basically how long our total program takes to run. And then as you go down, you can see individually where things go. And so here is a really important one here, which is the regex from string, which is the build operation. And it's taking 180,000 cycles right here. If you kind of go along the same level, you can see there's also regex search taking about 4,000 cycles. Looks like this is more regex search kind of stuff here. There's the commit function, which is taking about 9,000 cycles. And then shot compress, which basically this is where we're compressing, where we are digesting taking a hash of the haystack, is about 23,000 cycles. And this view here as well, you can click on things and it will kind of it'll let you dive deeper into each little part of it. And just in general, I highly encourage you to install this tool, check it out. It's really useful. I use it a lot. I've used it a lot in all my performance work. And we'll actually use it right now to kind of talk about how you actually might improve things. Let's take a time. Let's see. So I guess let's talk about what you might do to improve things. So basically, the first thing you'll notice here is that the regex construction is taking up about 70% of our time. So see, if we're doing profile work, we don't want to focus on anything really. This is like the main thing we want to reduce. So see, if we can possibly reduce this work here, we definitely want to do it. That will basically improve our program speed by a ton. And in this case, let's say we're working on an application, and there's other, you can do this in multiple ways. You could, have a library that compiles regex extensions at compile time. You could pass them in a serialized form. You could use pause resume, which is a feature of the zkVM, allows you to do work, pause the zkVM, and then resume later. But today we're going to talk about let's just remove that entirely. Let's say we don't actually need to do full regex search. Substring search is just fine for us. So we're actually going to reduce the functionality of our program to actually make it go faster. I'm going to, for this one here, I'm just going to go ahead and check out my other commit, which is up here. So I'll show you the diff first. Oops, sorry, trying to make it bigger. Again. Okay, so here basically we'll see that what we're going to do is we're going to remove regex from, oops, let's see. Okay, switch the colors. So we're going to remove regex from our guest application, and we're just going to replace it with substrings. So now there's no more regex in our application. And we're going to run it again. We're going to run that application again. And so there are four currents of foo in the string. We're going to run go tool again, or pprof again. And we'll see immediately that, like our program time is now 60,000 cycles, 7,000 cycles instead, way better. And they have different bottlenecks now. And so now, look, if you're going back in this optimization loop, you'll see that the biggest thing here again is compress. So this means basically that SHA-256 of the haystack value in particular is now taking basically the majority of our time. And one of the reasons for this basically is that actually this here, we're using the SHA-2 crate here, and we're just using the software implementation. We're not using any kind of like special features, whatnot, but the zkVM actually includes a hardware accelerated version of SHA-256. So basically, in order to actually activate it, we're going to change this dependency here to be to use the RISC Zero fork of SHA-2, the SHA-2 crate. So github.com, RISC Zero, Rust crypto -hashes. Tag we want to use is SHA-2 version 10.6. Oh, sorry, 0.10.6 RISC Zero. That's 0. Not what you remember all this. I did this recently, so I remember it personally. But you can look it up on our GitHub, honestly, or obviously. This repo here. And let's run the program again. Oh, oops, .com. Just apply coding. The BRF again. For the flame graph. And I can see that in total we're now using 40,000 cycles, so it's getting better. And that SHA compress time has now effectively gone away. I can't actually find it anymore. I'm sure it's here. Oh, wait, I think it's well, that's it. That's in finalize. Oh wait, where is it? Oh, oops. Oh, there it is. So here is the top time tank. So that's 1,500 cycles. That's much better. Okay, So I think there's one more as well. Oh, no, that's all of them I wanted to show you guys today. Basically, like this kind of optimization loop is the core way you're going to want to do your work for optimization. This is true both in zkVM and also in general, like outside programs as well. You know, you profile your program, look at what's taking the most time. Think about if you can reduce this time spent there, and then keep on once you've done that, reprofile again, and just keep on doing this loop over and over again. This is kind of the core loop that you're going to use to optimize your guest programs, which is why I want to spend time actually like really showing that. Okay, so now that we talk about general purpose techniques here, let's talk about the key differences between the zkVM and CPU. So sometimes these key differences are going to be very important to optimizing your programs further. There are many ways in which the zkVM has different qualities than a physical CPU in terms of its execution. All right. So the first thing we're going to start with, we're going to kind of go through a list of these. The first thing we're going to start with is that most risc-v operations in the zkVM take exactly one cycle. This is very unusual compared to most CPUs and ISA implementations. On a physical CPU, a divide operation takes about 15 to 40 times as long as an addition. So basically 15 to 40 cycles. On a zkVM, a divide only takes 2 times as long. It only takes 2 cycles. If you're also, furthermore, an add and a multiply both take exactly 1 cycle. So if you're thinking about optimization, and you have the opportunity to basically trade, let's say a multiply for a couple of adds, let's say it's like a multiply by 3, and so you want to decide like, okay, well I could do that in 3 adds or 2 adds instead. Add a value to itself and itself again. That's multiply by 3. Well, that's actually slower in the zkVM than a multiply, which is unusual compared to most physical CPUs. Furthermore, addition as well, or division as well, is kind of has the same qualities, has similar qualities. More generally, addition, comparison, jump, shift left, load, and store operations all take exactly 1 cycle. Bitwise operations, division, remainder, and shift right take 2 cycles. That's basically, and so all the basic operations take either 1 or 2 cycles in the zkVM. Another one that I will call here is that bit operations are actually slower than arithmetic operations. So that's something to keep in mind. Another key difference is that memory access, costs 1 cycle, except when it doesn't, but which I'll get into in a second. But this relative to physical, like the way physical CPUs interact with physical memory is very different. So see, physical memory takes 100 to 150 cycles or so, just as a rough estimate, to access. It's also asynchronous. Basically, when the CPU tries to load a value from memory, the CPU will keep doing other work in the background. And this latency, basically going the round trip time to memory, is actually a very, very major point of optimization in traditional programming. So if you're accessing the same value multiple times, it is no faster, or basically in the zkVM, it only ever takes 1 cycle to access, and so it's in terms of cycles, it's very fast. The exceptions to this are for paging operations. So the first time, basically, so memory in the zkVM is divided into 1 kilobyte pages. So basically, it's about 192 megabytes is total user addressable memory. That is divided into 192,000 1 kilobyte pages of memory. Every time you access a page for the first time, it needs to be loaded or paged in. And before the program ends, any pages that have been written to need to be paged out. The reason one of the reasons we call it pagings and kind of paging is that this is kind of analogous to the way that a computer will read and write memory pages to disk in order to save them either during hibernation or if it runs out of memory. And so basically, when you think about the zkVM, while it's executing continuations, essentially the way it does is that on each segment, it basically boots the zkVM, boots the computer at the start of the segment, and it shuts down, and it kind of goes into hibernation at the end. And when it hibernates, basically it needs to write all of its memory out to disk effectively. And so that's what we call it paging. And the first time you ever access a page in a segment, it needs to be loaded for the first time. And the last time, basically before the program ends, you need to write it back out again. So you can pick it, so you can load it back again in the new segment. This paging operations are done by a Merkle tree, which is basically involves a lot of hashing. This is why it takes 10 cycles. So a paging operation takes a variable amount of time. It takes between 1,094 and 5,130 cycles. The average is about 1,130 cycles per page, or about 1.35 cycles per byte. That average is if you were to read all of memory from 0 to 192,000, then you would end up with that average number of total time spent. So in this way, repeatedly accessing the same memory is indeed somewhat cheaper than accessing a very wide range of memory. And so this is kind of the main thing to think about. If you're talking about memory access, actually accessing memory itself repeatedly is not really a problem at all. But accessing a very wide range of memory might end up costing you more, quite a bit in terms of paging cycles. Another important thing to note is that the zkVM does not have native floating point operations. So each unlike most CPUs nowadays, it basically which implement IEEE floating point in hardware. So that basically so that floating point operations are almost as fast as integer operations. The zkVM does not have that implementation. Floating point is instead implemented in software by the compiler. And so each operation turns into about 60 to 140 cycles of risc-v integer operations in order to actually implement IEEE floating point in software. So whenever you can, just try to avoid floating point. And that's not always possible, but if you could ever have a chance basically to use fixed point or use integers instead, definitely go ahead and do that. Also, that's probably good general advice. Avoiding floating point is almost always the right call whenever you can avoid it. Unaligned data access is more expensive. So what is kind of an aligned versus unaligned data access? Well, basically, the first thing you're going to talk about is what a word is. So a word is a standard unit of data for operations. So in a 32-bit ISA, like RISC-v 32 bits, then a word is 4 bytes, which is 32 bits. And a 64-bit ISA, like x86 _64, basically, what most Intel processors are nowadays, or AMD 64, the word size might be, you'll end up with a word size or you end up with a pointer size that is 64 bytes, or 8 bytes instead. But basically, there's kind of this idea of a standard size of unit size of operation, which is in the case of RISC-v is going to be 4 bytes. When a value in memory exists at an address which is a multiple of 4 bytes, then it's considered aligned. If it's offset by and is at an address that is not multiple of 4 bytes, so basically, let's say it's at address something 1, the last digit is 1, then it is an unaligned access. The processor can only issue loads and stores of memory at aligned addresses. And so if you want to read from an unaligned address, you actually end up having to read multiple times to implement this. So reading U32 value, so a RISC 32-bit inside integer, normally costs 1 cycle if it's aligned. But if it's unaligned, it costs 12 cycles to access in the zkVM. that's just the way that that's part of the software implementation of unaligned reads. So in general, well, sad. Okay. In general, the compiler will help you make sure all your reads are aligned. Anything you allocate will be aligned by default, and so will so will fields that the compiler puts into a struct. But if you basically you're slicing into byte arrays, or if you are doing something or if you're making structs that are very tightly packed with U8s or smaller values, then you need to be careful and make sure that you are not incurring extra cost for unaligned data access. So when another kind of performance tip here is that we have this inv read function, basically just the standard way to read data into the zkVM. You see it in our desk program here. We use it. No, that's like this one. We use it here to read 2 strings from the host, and this inv read function does 2 things. First of all, it actually copies data from the host, and then also it deserializes it. That's why we're able to get a string value as the output rather than just an array of bytes. On the host side, this is done by basically using the executor inf builder dot write function. So we write the needle, and then we write the haystack. And those basically we correspondingly we read the needle, and then we read the haystack in a guess. If you're ever working with byte data, if you're ever working with data that is exclusively just a slice of bytes, then you can avoid the overhead of deserialization, which requires copying your input by using the INF Read Slice function. That's like the images I had in the slide are not loading. Sorry about that. Here it is. So you can use INF Read Slice or stdio read, which do not do any kind of deserialization. So showing you back on this example here, I might change this to a vector. Let's say so. Let's needle equals vector 8. Sorry. It's like this. And then I can use read slice. With immutable reference to this vector. And basically get the actual input data. Now, what I'm not doing here is that you actually do need to deal with the sizes of things. And it's a little bit more overhead to actually do this. Basically, here I would need to actually say like needle dot resize, and resize it up to the size of data I expect to receive. And so it's a bit more work to do this, but ends up being quite a bit more efficient when you don't need to do deserialization. In the code here, I wonder if you can see it. I think, so in this case here, the cycle count for the reading in this data is actually fairly small. It's about 1,000 cycles out of a total of 39,000 cycles. So it's probably not worth doing. And I wanted to I want to emphasize that because in general, for small input data, this optimization is not worth it. Basically, it's going to end up making it more complicated, and deserialization actually is something that is rather helpful for your use cases. So this is an example of when you have very large input data, it might end up being worth doing. So this is again something that basically, if you read the profile and then see where you're actually spending time, it is very likely, or is very possible that for large input data you are spending most of the guess time in reading input and deserialize input. And this is, I'm using read slice instead of read is a way to get around that deserialization cost and copying cost. Another technique you can use is that when you have large input data, and you only need part of it, then you can try using a Merkle tree to basically allow partial access to your data while still maintaining a hash of the root. So in the Where's Waldo example that we have, we use this. We use Merkle trees to access a region of an image in order to do image cropping. This greatly improves the total time this program takes, because it allows us to only read the thing that we need instead of the entire image, which would be extremely expensive. So Merkle trees are also a very useful technique. When you the characteristics to look out for is large input that you only need part of, then in that case, it's maybe worth Merkleizing. So the question basically is like, what would you consider to be a large input data? So that kind of depends on where your cycles are going. So see, if you have a program that takes 50 million cycles, and you're spending 30 million cycles on reading input data, which might be you probably, in order to get there, you probably have to be on the order of definitely hundreds of kilobytes or a megabyte or more of input data. But this basically is like the best thing to do is just be guided by your profiler here. Basically, if you're thinking like maybe 100 kilobytes or megabytes, then that's probably an area in which basically you start to think about like, what are some more advanced techniques I can use to reduce the amount of time it takes to read this data. Of course, I say that I say that for a 50 million cycle program, but also if your program is taking 1 million cycles and you really want to keep it to under 1 million cycles, then the same might apply. So basically, the input data might only be let's say like 10 kilobytes, but that may be large enough relative to your program's total runtime that it's worth doing things like Merkleization. One thing's worth mentioning here as well is a hash evaluation is using the SHA-256 accelerator is a relatively cheap thing to do. So basically, it takes about it takes six cycles for initialization, and then 68 cycles per block per hash block, which is 64 bytes. And so that's 72 cycles per block is kind of a rough number you can use to think about like how long does it take to hash something. So relative to reading large data, hashing part of that data is much cheaper. There's also, in the optimization guide I mentioned before online, we have this neat table down here of cycle counts for all of the RISC-V operations plus our equals. So this is useful as well. All right. So, and this actually gets us to the next thing, which is that the RISC Zero's RISC-V implementation includes a number of extensions. Two of those extensions are a SHA-256 compression circuit and a 256-bit modular multiplication circuit. So using these, you can do some accelerated cryptography. The SHA-256 compress function obviously is very useful for hashing. So whenever you're hashing data, like you saw in our example before, you can use an accelerated implementation of SHA-256 to greatly reduce the amount of time you're spending hashing. So basically, for example, in our example before, we went from about 23,000 cycles to about 1,000 cycles for hashing. And then the 256-bit modular multiplication accelerator is especially useful for elliptic curve operations. In order to actually support this usage, we maintain forks of a few common cryptography libraries. In particular, we have a fork for the Rust crypto SHA-2 crate, the K256 crate, which implements SECP K256K1, which is kind of the Bitcoin Ethereum ECDSA curve. We also have an accelerated implementation of ED25519 which is used for ED-DSA signatures and other operations. And we also have a fork of the crypto Bigint crate for general purpose Bigint operations as well. Basically, any 256-bit module multiplication is the operation that is accelerated, but that produces a really big advantage. So, for example, if ECDSA, if you're doing ECDSA signature, if you're verifying ECDSA signatures in the guest, it goes from taking about like 6 million cycles or so to taking a little under 1 million cycles in order to verify an ECDSA signature, which is nice. We also saw this in the example before, kind of calling back there, when I replaced this SHA-2 implementation with the RISC Zero fork. That is the SHA-2 crate that we forked to basically allow you to have the same API, but with acceleration. One thing I want to note about this, though, is that you don't assume that cryptography is too expensive to run in the zkVM without it. So, as you know, in the example we had before, we were running SHA-2 with just software implementation, no hardware acceleration, and we saw that it took about 23,000 cycles, which about increased our total program time by runtime by about half, but still somewhat reasonable to do. And other notable examples is that our Zeph implementation, basically, so our zero knowledge EVM implementation, uses Keccak without an accelerator. It's only a software implementation of Keccak, but still is has fairly fast proving times. Additionally, pairing operations and RSA signatures both work in the zkVM, and we've used them in examples before without major issue. So, if you're doing cryptography, the accelerators can be very helpful, but they definitely are not necessary in order to start working with cryptography. Another notable, kind of going back to the topic of memory, memory access in the zkVM is synchronous. So usually in a physical CPU, when it's waiting for memory access, it'll keep doing work. This gives rise to things like speculative execution, out of order execution in general, lots of other kind of interesting techniques implemented in the CPU, all designed to keep the CPU busy while it's waiting for memory access. Memory access in the zkVM is entirely synchronous. It stops and waits for memory access while it's before it continues working on anything else. And in general, and as a practical matter, this means that memory prefetching and other techniques people use to take advantage of the asynchrony of memory access do not help performance in the zkVM and can hurt performance in the zkVM. Similarly, all execution in the zkVM is single-threaded. The zkVM essentially has like one core and one thread of execution. Using async routines, using locking, using atomic operations will not help performance, and basically will only cost extra cycles. And kind of another angle on this as well is that the zkVM has no pipelining or instruction level parallelism. Modern CPUs are designed to execute many instructions at once. So basically, you might have an ALU that can handle, let's say, 16 additions at once, and it might actually be running multiple instructions of your program at the same time. In fact, it generally is always modern CPUs are almost always doing multiple operations at once. The zkVM executes one instruction at a time. And so reordering instructions, avoiding branches, other techniques designed to keep the pipeline full have no effect on the zkVM performance. In general, kind of all these three things, that's the synchronicity of the zkVM they're implemented this way because there's no need for it. The zkVM basically the proof performance is bottlenecked by proving time. Implementing some kind of asynchrony would not help the zkVM performance overall. So one of the things, like, kind of moving out to a bigger picture here, the main reason people are generally interested in optimizing guesses is actually to get faster proving and lower cost proving. Another way to get lower cost proving and faster proving is to use hardware acceleration. So RISC Zero currently implements support for NVIDIA GPUs. And we previously had support for macOS Metal, which we call the hardware accelerators inside Mac laptops and Mac machines. That support is currently not supported. Basically, there's been some compiler changes recently to the Metal that have broken that support, and it is currently not functional. So we do still support it for NVIDIA GPUs. If you want to use an NVIDIA GPU as an accelerator, then installing RISC Zero with cargo binstall will give you a version of the RISC Zero VM with CUDA support compiled into it. You also will need the CUDA runtime drivers on the machine that you're going to run the program on. If you're building RISC Zero from source, you can build in the CUDA feature with the CUDA feature flag. You will need the CUDA toolkit on your system. So one last thing I'll leave y'all with this is like some quick wins. So basically, if you want to try to increasing the performance of your application, one of the first things you should try is just twiddling some compiler flags. So there are various, if you look at the RISC performance book, it has some great information about this. But doing things like setting LTO, which is linked time optimization, to thin or fat or true, those are all useful kind of things to check out. And sometimes thin is faster than fat. Fat is when it does more heavy optimizations, but into the larger binary. And so larger binary basically increases the runtime as well. Similarly, optimization level 2 is sometimes faster than optimization level 3. S and Z, which are both size optimized, are also useful settings to try as well as messing up the code gen unit section. So there's a ton of different compiler flags that Cargo and RISC expose, and it's worth trying them out. Additionally, if you ever need a map data structure, the B-tree map in the zkVM is much, much faster than the hash map. This is partially related to the fact that branching and memory access are relatively cheap in the zkVM compared to the physical CPUs, and so unlike a lot of times on physical CPUs, B-tree map, which is more ends up being faster. If you need hash data, make sure to use the accelerated SHA-256. Just a really easy way to reduce cycle counts. And kind of reducing copying and deserialization of data is useful to look out for. And in conclusion, basically, kind of things to remember about how to optimize your guest. Profile your guest to figure out where the cycles are being spent. Start by applying general purpose optimization techniques. Then apply knowledge of the zkVM internals to optimize even further, and continually reprofile and repeat this process just in a loop. Just step 1, 2, 3, 1, 2, 3. Profile step 1, and then keep on trying do new optimizations to see if you can get cycle counts down further. That's everything. Any questions?
I've got a quick question if you don't mind. Can you hear me all right? I'm just using a different mic.
Yeah, I can hear you.
Oh, perfect. So yeah, I just have a question around basically implication on like the size of the binary towards like the actual like proof size? Like, does it just come at the cost of like basically wall clock of proving time, or does it actually like affect how large the proof is, or is this kind of just like a static cost?
That's a really good question. It's the binary size has no direct effect on the runtime, either cycle counts or proving time. What it can affect is it can increase the number of cycles your program spends if your binary is more spread out across memory. So I mentioned that the first time you access a page in memory, you have to pay the page in cost. And if your program is more spread out, then you're accessing more pages. And so therefore your cycle, your page in cycles may increase, thus increasing your total runtime. So it's kind of like, it's a little bit of an indirect effect. And so it may not always happen. Sometimes like it's really something you have to kind of like try it out, try optimizing your program in different ways and see what happens to the runtime. And then on proof sizes are constant, at least once you use recursion, which is open source and available in the general implementation. So the way things will work is that with continuations, your program will be proved one segment at a time, and you'll have a proof for every segment. And then from there, you can compress all those proofs into one proof using recursion.
So, yeah, it makes a lot of sense. Yeah, that makes a clarification there. I guess I was just curious in the case, like outside of kind of continuations, if there's like a very small program, it still is the same size as something that uses the like max cycle count of one continuation segment. It is kind of a little bit out of scope of what you're talking about, but maybe I'm just like misunderstanding some of the core primitives.
So that actually is true, that without recursion, and you have a one segment program, the larger cycle counts have an effect on the proof size. It's not linear. Basically, there's kind of a baseline cost, and then it kind of increases as you scale up the number of cycles. But basically, so a program that uses a power of 2 of like 2 to the 24, so basically it's like 16 million cycles. It might have a receipt that's about twice or 3 times as large as a receipt as 2 to 16 or 32,000 cycles. Once you use recursion, all receipts are going to be the same size, and the recursion receipts are smaller than the original receipts in the first place. So basically, with recursion, proof sizes are always going to be constant. Without recursion, basically, you're right that they do vary somewhat.
Awesome. Thanks for the clarification.
Mm-hmm. Any other questions?
There's a question in the chat about, is there a way to know how much memory you're using in the guest?
That's a good question. There is not a built-in way to do that. That would be very interesting to do, though. That'd be a very interesting one. So there's not obviously that. You can, there's not a direct way to that. You can do some estimates. Cargo has good support for printing the size of your data structures. You can estimate basically how many of those you have in memory. There's no direct and straightforward way to do it. We don't have like heap profiles, for instance, as a supported feature yet.
Oh, one thing to note about the heap is in the zkVM is that we use a bump allocator. So we never really free the memory. So I guess another way to monitor it is to kind of like log out, like whenever that allocator is called, just like have some sort of log that says, okay, now we're at this much.